Hello there, and welcome. Tonight, we're going to peel back the illusion of the stars, because those twinkling lights, they're not what they seem. What looks like a cosmic sparkle is really a distortion, an ancient signal flickering through a churning sea of air, gravity, and light. Stars shimmer, not because they want to, but because our universe bends, sways, and breathes. The twinkle is just the surface. Beneath it are secrets, atmospheric rivers, warping space-time, stellar ghosts, and gravity so intense it curves starlight itself. So, if you've ever stared up at the sky and wondered what's really going on up there, you're in the right place. And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or pressed the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time it is in your corner of the night. It's oddly fascinating to see where people are drifting off with us, scattered across the world like stars across the galaxy. Now take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. High above you, the stars seem to shimmer with life. They blink, they dance, they pulse gently in place, like distant candles flickering on a faraway shore. It's one of the oldest sights known to human eyes, long before cities, before fire, before language even had a name for light. We looked up and saw those tiny glimmers swaying in the dark, and we called them alive. But stars don't actually twinkle. If you were to leave Earth float far above its clouds, its winds, its invisible skin of air, you would notice something strange. The twinkling stops. Out there, in the still silence of space, stars become steady. Their light pierces, the void without flicker, sharp and constant, like pinholes in a perfect canvas. It's not the stars that change. It's what stands between them and you. Every night, above your head, the atmosphere hums with quiet motion. Though it feels invisible and still, it is in constant turbulence. Air shifts temperature by the moment. Currents rise and fall. Layers blend and ripple like water stirred by an unseen hand. And it's through this living veil that starlight must travel. A beam of starlight begins its journey far from here, sometimes from hundreds or even thousands of light years away. It travels in silence across empty space, unchanged and unbroken for eons. It moves faster than anything else we know, unbending through cosmic voids, slicing through gravitational fields, slipping past dust, planets, and comets. For nearly all of its journey, it remains pure. But then, just before it arrives, it meets the sky. The Earth's atmosphere is not one smooth shell. It's layered like a shifting glass of liquids at different densities, stirred by heat, pressure, weather, and time. Warm air rises, cold air sinks. Wind bends and folds these layers into spirals and swells. The boundary between night and day reshapes them each evening. The light that once streamed smoothly from a star now enters this soup of motion. And that's where the flicker begins. The technical word is scintillation. It means a rapid variation in brightness and position caused by the movement of air. As light passes through these unstable layers, it's refracted, bent slightly, redirected, disturbed, but not just once. It's bent again and again, differently at every altitude, by every new thermal gradient. One moment, the light reaches your eye directly. The next, it's nudged slightly off course. The result is a stutter, a brief, almost imperceptible flick that our brain interprets as a twinkle. To us, it feels like the star is trembling. From the ground, this phenomenon looks enchanting. But it's a trick of proximity, a distortion from standing inside a moving medium. It's like looking at pebbles beneath a rippling stream. What you see depends less on the stone and more on the water moving between. And in this case, the stream is the air you breathe. The thickness of the atmosphere plays a role too. When a star hangs low near the horizon, its light has to pass through a much greater volume of air than a star directly overhead. More air means more distortion, and so the twinkle intensifies. Those low-hanging stars flicker wildly, often changing color as their light bends through different layers. But high above, when a star is nearly overhead, the air is thinner, cleaner, steadier. The flicker is softer there, sometimes barely noticeable at all. Not all twinkles are equal. Bright stars, like Sirius, seem to shimmer the most. Their intensity makes every shift more visible, every dip in brightness more dramatic. Fainter stars flicker too, but we don't always catch it. Their changes blur into the night, subtle and ghost-like. Astronomers have spent centuries trying to see past this illusion. Early stargazers assumed the twinkle was part of the star itself, its heartbeat, its breath. But modern observatories know better. They seek high ground, mountaintops above much of the thickest air. They use adaptive optic systems that measure the distortion in real time and adjust mirrors to cancel it out. Some even create artificial stars by shining lasers into the upper atmosphere, letting computers map and compensate for the twinkle. Anything to see the sky as it truly is, because beneath the flicker, there is clarity. A star, in truth, is a blazing sphere of plasma, often hundreds of times larger than our sun, sometimes tens of thousands of times brighter. It does not flicker, it burns. It hurls light into space with perfect consistency, the result of nuclear fusion humming deep in its core. That light radiates outward in all directions until, by staggering odds, a single ray brushes the side of Earth and lands, at last, on your eye. And still, that moment is flawed by atmosphere, beautifully flawed. Without the twinkle, the night sky might seem colder, more clinical. But the atmosphere adds a certain intimacy, a reminder that we're not observing from nowhere, we're here, at the bottom of an ocean of air, looking out through a living lens. You could almost think of it as a conversation. The star speaks, the air stutters, and your eye listens. What you see is not what the star is, but what the air allows. Each flicker a stammer, each blink a translation. You're not just seeing light. You're watching the sky speak it, and the more you look, the more you notice the rhythm, a kind of atmospheric heartbeat pulsing through the stars. No two twinkles are quite the same, because no two patches of sky are quite the same. Even on windless nights, the high-altitude air is moving, always moving, and so the stars above you perform quietly, slowly, just for you. But know this, the twinkle isn't real. It's an illusion caused by our position, our atmosphere, and our perception. A lie the air tells on the star's behalf. And somehow, that makes it feel even more alive. Out beyond the air, the clouds, the pressure, and the pull of weather, the stars change. Or rather, they don't. Their shimmer disappears, their flicker fades, and what's left is something harder, cleaner, and far more precise. Out in the silence of orbit, above the trembling lens of Earth's atmosphere, stars do not twinkle. They blaze steadily, sharp and quiet, like holes cut through the sky. Astronauts have said it's one of the first things they notice, the stillness of the stars. From the window of a space station or the shadowed side of the moon, the stars don't seem alive in the same way. They're motionless, piercing, no flickering, no shimmer. Just a sky punctured with perfect, unwavering light. To the human eye, this stillness can feel strange. We're so used to the sparkle, so used to interpreting those small, rhythmic pulses as signs of movement, of life. In space, the illusion is gone. The stars become what they are, remote, radiant, unblinking. This is why telescopes go to space. Down on Earth, even the most powerful telescopes have limits. The atmosphere warps and wavers the light that reaches their mirrors. No matter how large the lens, how finely tuned the equipment, the air between here and the stars acts like a veil of water. The view is never entirely still. Even short exposures can blur. Details get lost in the shimmer. That's why astronomers climb mountains, build observatories in deserts, or drift balloons into the stratosphere. They're chasing clearer air. They're trying to get closer to that invisible line where the atmosphere ends and the universe begins. But the atmosphere always wins unless you leave it behind entirely. The Hubble Space Telescope was one of the first great eyes we placed in orbit, and when it opened its gaze in 1990, the difference was immediate. Suddenly, stars weren't soft points. They were sharp, finely etched. Galaxies didn't blur together like mist. They revealed their arms, their cores, their hidden structures. A sky that once looked painted became one made of detail, and all of it without a single twinkle. The flicker, it turned out, had never belonged to the stars. Then came the James Webb Space Telescope, far beyond even Hubble's reach. Placed at a stable point beyond the moon's orbit, shielded from sunlight, cooled to near absolute zero, Webb doesn't see Twinkle either. It sees in infrared, in heat, in the long, quiet waves of ancient starlight. Its images are impossibly still. When it looks at a star, it sees not only the star's shape, but its spectrum, its temperature, its chemistry, its motion, its past. It doesn't blink. It analyzes. It listens with perfect patience. From space, the sky is not alive with movement. It is alive with data. Back on Earth, though, our experience is different. We see a sky that twitches, glimmers, sways. We look up and believe the stars are fluttering like candle flames in wind. But it's not the stars that flicker, it's our air that dances and our eyes that try to follow. Twinkling is not just an atmospheric phenomenon, it's also psychological. Our brains are wired to detect motion, to assign meaning to subtle change. A faint dip in light, a flash of color, a momentary brightness. Our eyes leap to interpret it, and in doing so, they exaggerate it. The twinkle becomes more than physics. It becomes a story. This is why stargazing feels magical. It's not just that the sky is moving, it's that we think it's moving just for us. But in space, without air, without atmospheric distortion, without the push and pull of pressure and heat, stars become cold and consistent, not less beautiful, only different. Their light doesn't dance, but it does tell stories. It reveals motion, age, structure. Some stars brighten and dim with precise rhythm pulsars, variables, eclipsing binaries. But these aren't random twinkles. They are signals, timing mechanisms, celestial metronomes beating across light years. When we observe these stars from space, we can track them with extraordinary precision. We can measure their dimming down to fractions of a percent. We can tell when a planet passes in front of them, or when a companion star nudges their orbit. None of this would be possible through Earth's turbulent lens. The air would add noise, movement, doubt. But in space, the quiet is complete. There is no flicker to disguise the truth. Even for astronauts, adjusting to this stillness takes time. On Earth, we expect motion. The horizon sways with heat. The stars shimmer as they rise. Clouds twist light into halos. But in orbit, those cues vanish. Shadows are sharper. Light is harsher. The sky doesn't shift, it just is. And the stars, for the first time, show us how little we've truly seen. This is why twinkling is such a beautiful lie. It makes stars feel close, alive, soft. But the truth is they are distant, steady, and powerful. The flicker is ours. The shimmer is a flaw in the lens we live inside, yet we cherish it. We write poems about it, songs. Childhood wishes are pinned to it. Twinkle, twinkle, little star, we say, never questioning why they twinkle at all. The rhythm of that flicker has become part of our inner clock, and even though science has peeled back the illusion, revealed the cause, explained the physics, we still love the mystery, because sometimes illusion is what makes wonder feel personal. Out there, beyond our breath, the stars shine on, constant and undisturbed. They do not twinkle, they do not sway. But here, beneath the thin blue shell of air, we see them flicker like secrets, like questions, like the sky is whispering something just to us. And maybe, in that shimmer, we find something just as true as science. Not what the stars are, but what they feel like. From here, the air above you is not still. It may feel calm, especially on a quiet night when the wind has died and the leaves hang in place, but the sky is never motionless. It is layered and living, stirred by sunlight and shadow, pressure and pull. What seems like emptiness is a sea of constant movement. And through that restless ocean, the light of distant stars must travel. The atmosphere is not one single shell, but a series of invisible blankets, each with its own temperature, density, and rhythm. The lowest, the troposphere, is the air you breathe, the home of clouds and storms and weather that shifts by the hour. Above that lies the stratosphere, colder and thinner, where jet streams coil like great unseen rivers. Beyond that are even higher layers, the mesosphere, the thermosphere, and the exosphere, each more rarefied, each stranger than the last. These layers don't sit neatly stacked. They churn and swirl, colliding and overlapping like eddies in a great skybound tide. At night, when the sun has slipped away, the cooling earth exhales, the ground sheds its heat, and the air closest to it begins to cool. But not all layers cool equally. Some hold their warmth longer. Others chill rapidly. This difference in temperature from one layer to the next, this gradient creates bending points for light. Warm air and cold air have different densities, and when a wave of light crosses from one into the other, it changes direction ever so slightly. The sharper the gradient, the more the light bends. Now imagine a star, a single point of brilliant light from dozens, hundreds, or even thousands of light years away. Its light travels all that distance in a straight line, perfect, uninterrupted. But the moment it hits the upper edge of Earth's atmosphere, everything changes. That beam of light is now at the mercy of temperature, motion, and gravity. As it passes through these shifting layers, it bends. Then it bends again, then again, and again. Not in big ways, but in hundreds of tiny, cumulative ones. Each bend warps the star's position just slightly. Sometimes the beam arrives straight to your eye. Other times, it's deflected just enough to miss you entirely. What you see is a shimmer, a flicker, a soft and jittery glow. This is scintillation, the technical term for the twinkle. It's not caused by the star itself. It's not something happening in space. It's a result of the atmosphere warping the light as it enters your world, and it's always changing. Even moment to moment, the air shifts. High above you, the air cells expand and contract. Pockets of warmth rise through cooler surroundings. Turbulent currents twist like underwater whirlpools, redirecting the incoming starlight in chaotic bursts. Each twist changes what you see. A blink, a dimming, a sudden flare. To the naked eye, it becomes a kind of sparkle. But if you could slow it down frame by frame, you would see the star shift in brightness, in color, in location. Many times each second, the flicker is not uniform. It's alive with variation. Sometimes it's subtle, like a candle behind glass. Other times it's wild, especially when a star sits low on the horizon, and its light must pass through more of the atmosphere to reach you. From that angle, the star's light slices sideways through the thickest part of the sky, through more temperature shifts, more turbulence, more distortion. It can seem to pulse in red and blue, even dance. But it isn't the star that's changing. It's the ocean above you, rippling silently. Scintillation can be measured. Astronomers describe it in terms of seeing, how clearly stars appear through a telescope, how much their image dances or blurs. Bad seeing nights are full of motion, the starlight wobbly and smeared. Good seeing nights are rare, when the air settles just enough for starlight to pass relatively undisturbed. On those nights, the stars may not twinkle at all. They may sit steady and round, like the distant suns they are. But most nights, the twinkle returns, not because the air has failed, but because it is doing what it always does, moving, flowing, carrying heat and energy around the world. The atmosphere is Earth's shield and breath. It guards you from radiation. It holds in warmth. It brings rain, sound, and flight. But it also bends the cosmos. It distorts light from the ancient past. It smears the stars. And it does this constantly. There's a reason stargazers speak of nights as clear or not. There's a reason astronomers climb mountains to build observatories in dry, thin air. At high altitudes, the atmosphere is calmer, less turbulent, and thinner. There's less water vapor, less heat distortion, fewer chaotic eddies. The stars twinkle less, the images sharpen, but no matter how high you climb, you're still looking through moving glass, still seeing the stars through a veil of motion. Some observatories use lasers to fight this. They shine beams into the upper atmosphere, creating artificial stars, tiny points of light that act as reference. By measuring how these fake stars twinkle, computers can calculate the distortion in real time and bend telescope mirrors to cancel it out. It's a kind of visual noise canceling, designed to strip away the ripple and reveal the sky as it truly is. But even with the sharpest tools, even with algorithms and mirrors and high-altitude peaks, the atmosphere still hums, it still shifts, it still tells its story through every flicker. The sky above you is never at rest. Even when you sleep, the air turns. And when you look up, when you see that small glint dancing on the edge of sight, know that you are not seeing a star in stillness. You are watching its light perform, refracted, reframed, scattered, and returned, shaped by every swirl and shadow of the atmosphere. Scintillation is not a flaw. It is a footprint, a record of the ocean between you and the stars. And in that ocean, the sky sings quietly, bending the past into a shimmer. When we talk about stars twinkling, we're usually talking about something we can see: a flicker of light, a sparkle in the distance, a tiny trembling point that dances against the black. That kind of twinkling belongs to the world of visible light, or what's known as optical scintillation. It's the kind that flickers in poetry and songs, that soft pulse you catch out of the corner of your eye on a crisp, dark night. But twinkling doesn't stop where human vision ends. Even far beyond the spectrum of light our eyes can detect, stars and other cosmic objects flicker in stranger, quieter ways. In the realm of radio waves, there is another kind of twinkle, a hidden one. This one doesn't shimmer in the sky or sparkle through the atmosphere. It hums, it pulses, it stutters, through antennas and telescopes tuned to hear the universe instead of see it. And though it is invisible to us, its story is just as rich. Radio scintillation works on the same basic principle as optical twinkling. A signal often from a distant quasar, pulsar, or fast radio burst travels across the cosmos. Along the way, that signal passes through space that isn't empty. Even the vastest stretches of nothingness are filled with wisps of plasma, filaments of charged particles, and irregular clouds of gas that drift between the stars. This medium is known as the interstellar medium, and it behaves a bit like the atmosphere does for light. It bends and refracts the signal ever so slightly. It causes interference. It scatters waves. And when that signal finally reaches our instruments, we notice variations. Little hiccups in brightness, flickers in timing, strange dancing beats that don't always repeat. This is interstellar scintillation, a kind of cosmic echo shaped by space itself. One of the most fascinating places this occurs is with pulsars. Pulsars are remnants of massive stars that have exploded and collapsed into dense, spinning cores. As they rotate, they send out beams of radiation, like lighthouses in the dark. From Earth, we receive these pulses as regular, rhythmic signals. Some are so precise they rival atomic clocks. But as these beams cross the interstellar medium, They don't always arrive as expected. The signal can grow stronger or fainter. It can scatter slightly. The timing can shift. It's as though the space between us and the pulsar is murmuring back. Sometimes, multiple versions of the same signal reach us at once, delayed, redirected, or subtly warped. This creates patterns, interference, a cosmic shimmer that tells us not only about the source of the signal, but about the invisible terrain it crossed to get here. Scientists can study this radio twinkle to map the density and structure of the interstellar medium itself. It's like listening to echoes in a canyon and learning about the shape of the walls from the way the sound bounces back. And then there are quasars. These are galaxies with intensely active cores, supermassive black holes devouring matter and flaring brightly across the spectrum, including in radio waves. Quasars are so far away that their signals have traveled for billions of years to reach us. On their way, they pass through galaxies, dust clouds, magnetic fields, and plasma sheets. By the time they arrive, their signals carry the fingerprints of every twist and turn they've endured. They flicker subtly in radio wavelengths, often over hours or days, though sometimes faster. This flickering radio scintillation can be used to probe the nature of those ancient objects and the cosmic sea they swim in. What's remarkable is that this radio twinkle doesn't depend on our planet's atmosphere. It's not caused by heat or weather. It happens far beyond the influence of Earth, sometimes across thousands of light years. And while optical twinkling stops when you leave the atmosphere, radio scintillation follows you deep into space. Even probes traveling through the solar system can detect the subtle flutter of radio waves as they bend and scatter across the galaxy. To detect these twinkles, we don't use eyes. We use massive radio dishes spread across deserts and mountains, tuned to frequencies that soundless space carries best. We sync them together, turning the whole planet into one enormous ear. And what we hear, what we map, is a sky full of invisible flickers. Scintillation becomes a diagnostic tool, not a distortion, but a revelation. There's something almost ghostly about it. We are receiving messages not just from distant stars and black holes, but from the space between regions we cannot see, but which leave their marks in the signals they bend. The twinkle is the message and the medium both. A flicker in brightness might hint at a cloud of plasma drifting between stars. A delay in arrival time could reveal a denser knot of particles, or a subtle wave of magnetism sweeping through the dark. Sometimes, the flickering is so sharp, it creates beats fast, rhythmic pulses that shift with time, like the tuning of a radio station being slowly dialed across a long highway. These rhythms can be incredibly precise, and yet their cause is chaos. The randomness of interstellar turbulence, the unpredictable dance of particles drifting for millions of years. It reminds us that twinkling isn't just a visual delight, it's a universal signature. It's what happens when perfect, steady light or sound or signal meets an imperfect medium. And everywhere in the universe, mediums shift. Nothing moves in a straight line forever. Everything flickers eventually. Even the quietest parts of space, the cold voids between galaxies, are filled with structures too faint to see, but not too faint to disturb. Twinkling in the radio tells us they're there. It reveals their outlines, their densities, their invisible shapes, and sometimes, in the tiniest distortions, we find the presence of something new, something unexpected, a hidden star, a rogue planet, a massive structure with no name. This is the quiet hum of the universe, bent just enough to reach us with a flicker. We may never see these twinkles with our eyes, but we hear them, measure them, and trace their echo across the stars. And in doing so, we learn not only about where the signal came from, but about everything it passed through to get here. Every flicker is a path, every shimmer, a story, not just of light, but of everything it touched. On a clear night, when the stars shimmer like silver dust flung across velvet, there's often one point of light that refuses to play along. It doesn't flicker. It doesn't pulse or shimmer. It just glows steady, serene, unmoved by the air's invisible tides. It might be faint and red, like Mars, or bright and golden like Jupiter. It may even outshine the stars themselves, but it holds its place in the sky like a lantern hung on an invisible thread, unwavering even as the stars around it seem to dance. That's how you know it's a planet. To the naked eye, the difference between a star and a planet might seem subtle, especially if you don't already know what to look for. Both appear as points of light. Both rise and set. Both trace arcs across the sky as Earth turns beneath them. But watch closely, and a pattern emerges. Stars twinkle, planets shine. One flutters, the other holds. This contrast is not just poetic, it's physical. It has to do with distance, with size, with the way light behaves when it travels through the churning layers of Earth's atmosphere. Stars, even the closest ones, are unimaginably far away. The light from a bright star like Sirius has traveled over 8 years just to reach us. From that distance, even a massive, blazing sun is reduced to a single point. Not just to the eye, but to any telescope on Earth, Sirius is a pinpoint. That means when its light passes through the atmosphere, it's fragile. Any disturbance, any ripple of warm air, any sudden shift in pressure can bend that narrow beam slightly off course. Each change in the air becomes a lens, focusing or diffusing the light in real time. The result is a dance, a glitter, a flicker that never seems to rest. Planets, on the other hand, are much closer. Even though they're still millions of miles away, they are near enough that their light doesn't arrive from a single pinpoint. Instead, it comes from a tiny disk, a surface with measurable width. To the human eye, that disk is too small to resolve. It still looks like a dot, but to the atmosphere, that disk makes all the difference. Because when the air begins to ripple and warp, it doesn't bend all of the planet's light in the same direction at once. One edge of the disk may be bent slightly, upward. Another edge may shift down. These distortions average out. They cancel each other, or at least soften. The overall effect is stability. The flickering fades. The planet holds steady. This is known as the disk effect, and it's the reason Jupiter, though brilliant, does not twinkle like the stars around it. Its light, spread across a broader angle, is more resistant to atmospheric distortion. It's like shining a flashlight through fog instead of a laser pointer. The beam still reaches you, but the changes in the air don't distort it quite so much. That's not to say planets never flicker. When they're very low on the horizon, when their light has to pass through a thick column of turbulent air, even they can seem to shimmer. The effect is usually subtle, more of a soft distortion than a true twinkle. But it's there, a quiet reminder that no light escapes the atmosphere completely untouched. Still, when you look up and notice one star that refuses to sparkle, chances are you're not looking at a star at all. Venus is often the easiest to spot, hanging like a jewel just after sunset or just before dawn. She glows fiercely, sometimes even casting shadows when the night is dark enough, but she holds still, unblinking. The same is true for Saturn, for Mars, for the icy light of Neptune when it's visible. They shine with quiet confidence, unmoved by the air's invisible churn. It's a useful trick for anyone stargazing with the naked eye. If you're unsure whether a bright point in the sky is a star or a planet, simply watch it. Wait a moment. Let your eyes adjust. If it twinkles, it's a star. If it doesn't, or barely does, it's likely a planet silent, steady, and nearer than you think. This steadiness is one of the reasons planets make such good targets for telescopes. Even from Earth's surface, you can glimpse their shapes, their rings, their moons. Jupiter's 4 brightest moons, visible even through a small backyard scope, line up like beads on a string. Saturn's rings, delicate and pale, become real with just a bit of magnification. Mars may reveal hints of ice caps, of dusty plains. Because the planet's light isn't broken by twinkling, the view becomes clearer, more stable, easier to study. Meanwhile, the stars remain elusive. Even the largest telescopes on Earth see them as points. To truly resolve their surfaces, to map their shapes and count their storms, we have to leave the atmosphere behind. We have to build instruments in space, or we must use clever tricks, interferometry, adaptive optics to untangle the shimmer and reach the truth behind the twinkle. And yet, that shimmering veil gives us more than it takes. It adds mystery. It lends stars a kind of magic that planets, in their steadiness, seem to lack. One is a fire dancing in the wind. The other is a lighthouse, still and serene. So next time you're outside beneath a sky full of stars, take a moment to find the one that doesn't move, the one that glows without flicker, like a watchful eye or a quiet ember. That's a traveler from your own neighborhood, a world not so far away, sharing this corner of the solar system with you. And while the stars blink and whisper their distant songs, the planets wait in silence. Not flickering, not twinkling, just shining. When you look up at the night sky, you're not really seeing the present. You're looking into a deep, unfolding memory, an ancient slideshow playing in reverse, each point of light a frame from the past. The stars you see are not as they are now. Many are not even there anymore. What you see is the echo of something that once was, the final record of a long-departed presence traveling through space and time just to reach you. Light moves fast, faster than anything else we know. But even at that incredible speed, it takes time to cross the vastness between stars. The light from the nearest star system, Alpha Centauri, takes over 4 years to arrive. For Sirius, it's about 8. For stars further out in our galaxy, you might be looking at light that left hundreds, even thousands of years ago. And for some of the faintest stars barely visible to the naked eye, the light began its journey before the pyramids were built, before cities rose, before we knew what a star even was. That's the quiet truth of starlight. It's always late, and sometimes it's too late. There are stars that no longer exist, whose final acts ended in collapse or explosion centuries ago, but whose light is still traveling, still arriving. To us, they sparkle like any other, suspended in the black. But what we see is a ghost, an image without a body, a flame without a source. The star is gone. But the light, the messenger, has not finished its work. It keeps moving. It keeps showing us what once was. This isn't rare. In fact, the further out we look, the more common it becomes. Stars are born and die all the time, and the farther their light has to travel, the more likely it is that their story has ended before we ever got to witness it. But we don't see that ending. We only see the part still making its way through the dark, like a photograph floating downriver. And when that light finally enters Earth's atmosphere, it doesn't just arrive quietly. It twinkles. It's bent, scattered, refracted by layers of moving air. It flutters through the currents of our sky, catching the turbulence, the warmth rising from rooftops, the chill that settles in valleys. The twinkle, in these cases, becomes something more than just distortion. It becomes a shimmer layered with meaning. You are watching something that does not exist anymore, and not just watching, but watching it dance. It is one of the most poetic accidents of nature, the light from a long-dead star being bent and flickered by the breathing of our atmosphere, animated as if to say, "I'm still here." A flicker that reminds us not only of the light's age, but of the fragility of the source. It's a kind of cosmic illusion, one final performance by something that's already gone, framed by the very air we live within. Astronomers have long studied the timelines of stellar death, tracking the life cycles of stars by their mass, temperature, and luminosity. Some stars live for billions of years, others burn fast and die young. A massive blue giant, for instance, might last only a few million years before collapsing into a supernova. But if that supernova happened 1,000 light years away, and the light from the event is only just arriving now, then we on Earth are seeing the final breath of something that ended long ago. It's not just that the star is gone. The explosion itself, the death has already happened, but its story is still unfolding in our sky, a scene out of sequence. Every time you gaze at a star, you're reading a page from a very old book. Some pages are recent, still warm with the ink of the present. Others are worn and ancient, their words having drifted for centuries. You're seeing the stars not as they are, but as they were sometimes when humans first learned to speak, sometimes when no human eyes had yet existed at all. The further out you look, the deeper the history becomes. Galaxies seen through the Hubble and Webb telescopes are not just distant, they're ancient. We are seeing their youth, their birth, their fires just kindling, in light that took billions of years to find us. And in that light, every shimmer we see from Earth becomes something almost haunted. The flicker we notice with our eyes, caused by the movement of our air, adds a layer of immediacy to something impossibly distant. The light has traveled so far and so long, untouched for eons, only to be stirred into motion by the final sliver of sky. The last breath of Earth adds a flutter to the ancient. You might imagine the light, on its journey, crossing the cold of space untouched. It slips between stars, past drifting comets, and silent clouds of gas. Nothing stops it. Nothing slows it down. It remains unchanged until, in the final moments, it meets us. And the first thing it touches is the atmosphere, thin, restless, alive. That final turbulence turns the once steady light into a flickering signal, like a whisper passed from one mouth to another. It's easy to forget this when we stargaze. The stars feel immediate, permanent, alive. But some of them are just memories, and the shimmer we see, it might be the very last gesture of something long gone, softened and reshaped by the breath of the planet we stand on. The night sky is not only full of stars, it's full of echoes. And sometimes, those echoes sparkle. Gravity does not shout. It does not blaze or flare or flash. It bends, quietly, patiently. With a kind of invisible elegance, gravity warps space itself, pulling not just objects, but the very fabric that light travels through. The result is strange and subtle. A beam of starlight, crossing billions of empty miles, might not move in a straight line at all. It might curve, ever so slightly, like a river bending around a stone you cannot see. You might never notice, unless you look just right, with just the right lens, at just the right moment in time. Gravitational lensing is what happens when massive objects, galaxies, black holes, even clusters of dark matter bend the light from objects far beyond them. It's not a trick or illusion. It's the geometry of the universe playing out exactly as Einstein predicted. Mass curves space-time, and curved space-time redirects light. A distant star or galaxy, hidden behind some invisible mass, might appear stretched, duplicated, or distorted because its light has been lensed bent on its way to us, as if passing through a glass that was never there. This bending is not the same as the twinkling we see from Earth. Twinkling comes from turbulence, air in motion, temperature rising and falling, creating tiny fluctuations in how starlight enters our eyes. It's fast and jittery. Gravity's lens, by contrast, is slow, smooth, and precise. Instead of shimmer, it creates structure. Instead of flicker, it builds patterns. A star's light might form a perfect ring. A galaxy might appear, doubled, tripled, twisted into arcs and spirals. These shapes are not what the object actually looks like. They are what it becomes when its light is pulled through space that has been gently reshaped by the weight of something else. Imagine watching a single beam of starlight traveling across the cosmos. For millions or billions of years, it speeds along in darkness, untouched. Then, as it nears our corner of the universe, it passes close to a massive galaxy cluster. That cluster, too far and dim to see with the eye, is heavy enough to drag space inward like a deep well. The light from the star curves around it not because it's attracted like a magnet, but because space itself is no longer flat. When that light finally reaches us, It does not arrive straight. It's been bent, and what we see is a version of the star or galaxy that has been warped, stretched, and sometimes multiplied. Some of the most beautiful examples of this are known as Einstein rings, perfect circles of light formed when a distant galaxy lines up directly behind a massive object. The gravity of that object pulls the incoming light into a full loop, like a lens made not of glass, but of gravity itself. These rings aren't just beautiful. They are also rare and fragile. They depend on perfect alignment, and they show us both the source of the light and the mass of the lensing body, often a galaxy too distant to detect any other way. What's remarkable is that these warped images can masquerade as stars to the untrained eye. A tiny point of light, flickering faintly, might not be a star at all. It could be a distorted echo of a galaxy 10 billion years old, bent around something dark and massive in its path. In this way, gravitational lensing becomes a kind of cosmic mirage, bending the path of light so precisely that it hides and reveals at the same time. The key difference is that while atmospheric twinkling is temporary and ever-changing, gravitational lensing is persistent. A twinkle fades and flutters with the breeze. A lensing effect holds its shape across months, years, even centuries. The star might move slowly across the sky, the background might shift, but the pattern of distortion remains until the mass between us and the source changes or moves away. Scientists use this to their advantage. By studying lensing effects, they can map the mass of invisible objects, especially dark matter, which cannot be seen directly but still exerts gravitational pull. A faint arc of light in a telescope image can tell us about entire galaxies that are otherwise invisible. Sometimes, the light is magnified, giving us a glimpse of the early universe that would otherwise be too faint to see. In rare cases, gravitational lensing even creates multiple images of the same object. A single quasar, flaring from the heart of a distant galaxy, may appear in several places at once. Each image has taken a slightly different path through curved space, arriving at a slightly different time. In this way, we can watch echoes of the same event, a star's flare, a galaxy's collision, play out like a delay on an old recording. None of this twinkles. It doesn't shimmer like Sirius or pulse like a low star on the horizon. Instead, it bends in silence. The beauty is in the shape, not the flicker. It is precise and mathematical, but it is also deeply human, because through gravitational lensing, the universe allows us to see behind the curtain, not just the light, but the story of everything that touched it. Twinkling is the language of our atmosphere, fleeting and close, a ripple caused by wind and heat. Lensing is the language of gravity, slow and ancient, shaped by mass we cannot see, and forces we can only measure in whispers. And yet, both leave their mark on the same beams of starlight. One makes the stars dance. The other bends their path entirely. So the next time you see a faint, steady glimmer among the stars, one that doesn't flicker, one that seems out of place, it might not be a star at all. It could be a warped galaxy, or the shadow of a black hole, or a ripple in space from a mass you cannot name. It could be the fingerprint of gravity, stamped on light that has traveled for billions of years, not twinkling, but bent, and still, somehow, reaching you. Most of the stars in the sky aren't alone. They travel in pairs, sometimes in threes, sometimes in quiet, crowded families drifting through the dark together. We often imagine stars as solitary fires scattered across the night, each burning in its own corner of the sky. But that's more of a poetic truth than a physical one. In reality, stars are social. Nearly half of all visible stars are part of binary or trinary systems, two or more suns locked in gravitational orbit, circling one another in vast, elegant loops. From Earth, they usually appear as a single point of light. Too far away and too close together to resolve with the naked eye, they blend into what looks like one star. But their relationship is there, quietly influencing what we see. Their orbits pull and stretch the light in subtle ways. Their brightness fluctuates, and in some cases, they create patterns of flicker and shimmer that go beyond the usual twinkle of a solitary star. What we see is layered light from 2 or 3 sources, overlapping and interfering as it travels through the same patch of atmosphere. It's a kind of celestial layering. When light from multiple stars reaches us at once, the effect can be soft and smooth, or sharp and restless. If the stars are similar in brightness, their combined glow might pulse gently as they orbit each other, creating variations in intensity too small to notice unless you watch closely. But if one star is much brighter than the other, or if they pass in front of each other from our point of view, the changes can be more dramatic. These are called eclipsing binaries, stars that dim and brighten in predictable rhythms, like a heartbeat stretched across days or weeks. The atmosphere picks up on these fluctuations and adds its own flicker. The result is a shimmer with rhythm, a twinkle that has a pulse, and when there are 3 stars, the effect becomes more complex. Trinary systems often involve 2 stars orbiting closely, with a third circling further out. The inner pair might eclipse each other, while the third star adds its own light to the mix. As their positions shift, the total brightness seen from Earth can change slightly, and the flicker of that blended light becomes a dance between sources, interference, layering, and atmosphere combining to create something that looks simple, but isn't. Sometimes, the light doesn't just vary in brightness, it changes in color. If the stars in a binary system are different in temperature, say, one red and one blue, their light mixes in strange and beautiful ways. As they move in orbit, the dominant color can shift. The star might appear warmer one night, cooler the next. Not dramatically, not always noticeably, but just enough that, over time, it feels like something alive, something moving. This isn't just an illusion, it's the result of real motion, stars tugging at each other, gravity folding their paths into arcs and spirals, light curving along with them. The flicker we see becomes a record of their relationship, how fast they orbit, how close they pass, how much they differ in brightness or size. It's all written into the shimmer. And then there's the atmosphere, always adding its signature. When light from 2 or more stars arrives at slightly different angles, the turbulent air bends each path in as a slightly different way. Sometimes, this interference causes the stars to appear to flicker out of phase, like 2 separate lights switching on and off at different rhythms. In telescopes, this can create shifting shapes, elongated blurs, tiny figure eights, even momentary separations if the air clears just enough. For a moment, the illusion breaks, and you see them as they really are. 2 fires, not one. Early astronomers noticed this before they had the tools to explain it. Some stars, like Albireo in the constellation Cygnus, were known for their double nature, one golden, one blue. Others flickered strangely, brightening and fading in ways that didn't match the normal pattern of twinkling. It wasn't until centuries later that we understood what we were seeing. Systems of stars locked in gravitational embrace, revealing their presence not with sound or movement, but with variations in light. Even now, with powerful telescopes and satellites in orbit, we still rely on flicker to tell us who is alone and who isn't. Astronomers look for tiny regular dips in starlight, evidence of one star passing in front of another. Or they track subtle wobbles in position, signs that a star is being tugged by an unseen companion. Sometimes, the companion isn't even a star. It could be a planet, or a dead sun, or a black hole hidden in the dark. The flicker becomes a clue, a hint that there is more beneath the surface. When you see a star flicker just a little differently, when the rhythm seems strange or the shimmer seems uneven, you might be witnessing a story written by multiple suns. A family of stars dancing across centuries, their light tangled together before it reaches your eyes. You don't need to see them all to know they're there. The light tells you everything. It is layered, shared, and shaped by orbit. And the atmosphere, with all its restless motion, turns that complex story into a soft, trembling glow on the horizon. To us, it may still look like a single star, but behind that flicker are companions, bound by gravity, circling through the dark, each one adding its own thread of light to a pattern that began long before we looked up and will continue long after. High above the clouds, where the world thins and the silence grows heavier, something strange happens to the stars. They stop dancing, the shimmer softens, the restless flicker becomes a steady glow. To most of us, starlight will always seem to tremble. But for those who climb far enough, who build their domes on mountains so high that even the birds hesitate to fly, the stars begin to hold still. They shine more purely, more calmly, as if freed from the veil that cloaks them closer to the ground. This is why we build observatories on mountaintops, not just for the view or for the solitude, but for the sky itself. The higher you climb, the less atmosphere you must look through, and the less atmosphere there is between you and the stars, the less the light flickers, bends, and scatters. It's as if the air has loosened its grip, as if the stars are coming into focus, revealing what they were always trying to show you, but couldn't until now. Twinkling happens because the atmosphere is restless. Warm air rises, cold air sinks. Winds move in invisible layers, each with its own temperature, density, and speed. These shifting gradients bend starlight as it passes through them, changing its path by tiny degrees. From sea level, starlight has to travel through a thick wedge of this turbulence, which means there are more opportunities for the light to be jostled. By the time it reaches your eyes, the beam is frayed at the edges, bent slightly this way and that, creating the illusion that the star is moving or pulsing. But the higher you go, the less of this turbulence there is. Mountaintops sit above much of the densest, most unstable layers of air. The pressure drops, the temperature stabilizes, and the winds thin out. The stars above, these summits are still twinkling, of course, but only slightly, and only through the last few slices of atmosphere. The change is subtle to the eye, but profound to a telescope. What was once a flickering dot becomes a sharper, more reliable point. Photons arrive in cleaner lines, images become clearer. Astronomers call this effect seeing, not in the poetic sense, but as a measure of how much the atmosphere is interfering with a telescope's view. Good seeing means the air is still, the temperature is steady, and the starlight passes through with minimal distortion. Bad seeing means the air is turbulent, boiling with invisible movement, and the telescope's image wobbles like a reflection in a rippling pond. Even with the best equipment in the world, poor seeing can blur the details of distant galaxies, soften the edges of Saturn's rings, or make binary stars blend into one. That's why places like Mauna Kea in Hawaii or Cerro Paranal in Chile are chosen as homes for some of the world's most advanced observatories. Their peaks reach high into the dry, thin air, where clouds rarely form and artificial light is far away. Here, the atmosphere becomes less of a barrier and more of a lens, one that can be measured, managed, even corrected, because in addition to building high, we've also learned how to adapt. Telescopes today are no longer passive collectors of light. They fight back against the twinkle. They use a technology called adaptive optics, which measures the distortion caused by the atmosphere in real time and adjusts the telescope's mirrors to cancel it out. These adjustments happen hundreds of times per second. Tiny actuators reshape the surface of a flexible mirror, subtly shifting it to counteract the wiggle in the incoming light. The result is stunning. A star that once blurred and trembled across the screen becomes crisp, sharp, almost as if viewed from space. To guide these corrections, astronomers use artificial stars' laser beams fired into the upper atmosphere to create glowing points of reference. The telescope reads how the atmosphere is distorting the laser's light, then uses that data to adjust its view of the real star. It's like tuning a radio by watching the signal in a mirror, quietly, Precisely, the technology bends the mirror to unbend the sky. From mountaintop domes and adaptive mirrors, we get glimpses of clarity that rival even the Hubble Space Telescope. In some cases, ground-based observatories equipped with adaptive optics can produce images that are just as sharp as those taken from orbit, and they do it while staying rooted to Earth, where they can be maintained, upgraded, and expanded. Still, even these systems can't eliminate all distortion. They help us see through the atmosphere, but they don't make it disappear. The shimmer is part of the story. It always will be. But through careful placement, clever engineering, and the slow, patient climb into thinner air, we've learned to see past it to reach a little closer to the stars as they truly are. And something changes in the heart when the shimmer fades. When you look through a telescope perched on the edge of the sky, and you see a star not as a jittering flicker, but as a steady, unwavering light, it feels different. Not brighter, not louder, just more real. Like a whisper you can finally hear clearly. It's not that the stars stop twinkling. It's that you've moved closer to the place where the noise begins to fade, where the air holds still, and the universe begins to speak without interruption. Sometimes, when you look up long enough, you'll notice something curious. A star near the horizon doesn't just shimmer, it pulses in color. It flashes red, then blue, then green, sometimes even yellow or violet, like a jewel turning in candlelight. It seems impossible at first, like a trick of tired eyes, but if you keep watching, the colors keep coming, changing in rapid bursts, a strobe of chromatic light dancing just above the edge of the world. The twinkle becomes a flicker, the flicker becomes a flash, and the flash, somehow, becomes a spectrum. This isn't imagination. It's not a defect in your vision or some special property of the star itself. It's the atmosphere again, bending not just the direction of starlight, but its color. Light is not a single thread. It's a braided stream of wavelengths, each one corresponding to a color. Red light moves with long, lazy waves. Blue light travels with shorter, sharper ones. When that bundle of light enters Earth's atmosphere, it doesn't stay bundled for long. Like sunlight passing through a crystal or a glass of water, starlight gets scattered and spread out. And because each color bends by a slightly different amount, the star's light is broken into pieces, tiny fragments of color pushed apart by the moving air. From a high angle in the sky, when you look straight up, there's less atmosphere to pass through. The effect is mild. The twinkle stays mostly white. But near the horizon, where starlight must skim sideways through hundreds of miles of thickening air, the bending becomes dramatic. Different colors scatter in different directions, causing the star to flicker not just in brightness, but in hue. The atmosphere becomes a kind of shifting prism, constantly warping the light into flashes of red and blue. It's especially noticeable with bright stars like Sirius. Low on the horizon, Sirius often looks like it's on fire, its light flickering rapidly between crimson and sapphire, emerald and gold. To early stargazers, this made the star seem alive, as though it were burning with an inner flame that changed color as it flared. Even now, with the knowledge of refraction and optical scattering, the sight can feel magical. The physics explains the mechanism, but the beauty remains untouched. The effect is strongest when the air is unstable, when warm and cool layers mix, when pockets of moisture and density stack and shift in invisible waves. These micro-lenses in the sky refract starlight in ever-changing ways, turning a pinpoint beam into a kaleidoscope. It's not just twinkling anymore. It's atmospheric chromatic interference. But to the eye, it feels like the star itself is changing its mind about what color it wants to be. It's important to remember that the star hasn't changed at all. Its light is steady, constant, pouring out in every direction with the same spectrum it always has. What we see is not the star's truth, but the Earth's filter. We are looking through a shifting lens, one that warps color as easily as it warps direction. The star is still white, or blue, or yellow, depending on its temperature and type. But to us, down here in the soup of our own weather, it sparkles like a gemstone shaken in the palm of the sky. In a way, it's a reminder that every star you've ever seen has been interpreted through layers of something else. The color we assign, the shimmer we notice, even the position in the sky, all of it shaped by where we are, how we look, and what stands between us and the light. The flicker isn't just about the source, it's about the space in between. That space is never empty. It's filled with moisture, with dust, with heat. It moves, it breathes, and every movement, every breath, changes what we see. Starlight is patient. It will travel for 100 years without shifting a single degree. But in the final fraction of a second, just as it enters the shell of our atmosphere, everything changes. The stillness is broken. The path fractures, and color bursts from what was once a steady beam. There's something beautiful in that, something fragile. The knowledge that the red-blue flicker of a star on the horizon is not a defect, but a gift. It tells you the air is moving. It tells you light is being shaped, sculpted, turned by the hand of the planet itself. We see the cosmos, not just as it is, but as it becomes through us through the lens of our atmosphere, the chemistry of our eyes, the language of our perception, and sometimes the illusion reveals more than the reality. The colors don't last. As the star rises higher, the path through the atmosphere shortens and the flicker smooths out. The prismatic scatter fades. By the time the star reaches its peak in the sky, it may shine steadily, once more bright and constant, like a lighthouse above a still sea. But if you were watching, if you saw it rise from the edge of the earth, you would have witnessed that brief moment of color, the glint, the flare, the silent fireworks of refracted starlight. You might have seen a star blink red and blue, like a message flickering just for you. And in that flash of color, in that atmospheric shimmer, something ancient passed through something human. Not just light, but interpretation. Not just physics, but poetry. Because every flicker has a reason, and every color carries a story. A star's true color isn't always what it seems. To the naked eye, most stars appear white, or nearly so, some with a hint of blue, a whisper of orange, maybe a faint golden warmth if you're paying close attention. But in truth, starlight carries an astonishing range of colors, each one tied to temperature, composition, and age. Every star is singing a specific note in the spectrum, and yet from Earth, much of that delicate music gets muffled. What we see is filtered, blurred by the flicker of the atmosphere. The shimmer that makes stargazing so beautiful is also what hides the truth. Stellar classification begins with color, not artistic color, but spectral color, the precise wavelengths of light a star emits. Hot stars burn blue, cooler ones glow red, and in between lies a progression of types that scientists have sorted into categories: O, B, A, F, G, K, M. It's a sequence of heat, from the hottest and most massive to the coolest and dimmest. Our sun, for instance, is a G-type star, a warm, steady engine of yellow-white fusion. Betelgeuse is a red supergiant, an M-type star, vast and cool, and nearing its final breaths. Vega, brilliant and sharp in the summer sky, is an A-type star, burning hot with a white-blue gleam. These colors aren't just surface decoration, they are fingerprints. The hue of a star tells us its surface temperature, which in turn tells us how fast its atoms are moving, what kinds of nuclear reactions are taking place within, and how long it's likely to live. Color is how we decode a star's identity. But from Earth, the atmosphere bends and scatters that color. We know that light of different wavelengths refracts at different angles, and as starlight passes through pockets of varying temperature and density, it gets pulled apart and recombined in uneven ways. This doesn't just cause the flickering we see, it subtly shifts the apparent hue. A star that's blue at the source might appear white to us. A red giant might lose its warmth in the shimmer. And under heavy atmospheric distortion, a single star might seem to flash through a whole palette of colors that aren't truly there. It's not that the star's light changes, it's that we're watching it through a restless veil. That's why astronomers don't rely on the eye alone. To get past the distortion, they use spectroscopy, the science of splitting light into its component wavelengths with high precision. Instead of letting starlight hit the eye, they send it through a spectrograph, a carefully aligned prism or diffraction grating that spreads the light out into a long, detailed rainbow. Not the soft blur of color you see on a CD or in a soap bubble, but a fine, measurable spectrum filled with lines, dark gaps, bright spikes, each marking a specific chemical element or physical process inside the star. These absorption and emission lines are like a barcode. Hydrogen leaves one pattern, helium leaves another. Sodium, oxygen, calcium, all leave their mark on the spectrum. Even if the star is billions of light years away, even if its light has passed through galaxies, dust clouds, and Earth's own turbulent shell, its spectrum carries these imprints like scars, unblurred and deeply informative. From them, we learn not just a star's temperature and age, but its motion, its composition, even whether it has planets tugging at it with silent gravity. Spectroscopy is one of the quiet revolutions of astronomy. Where once we saw stars only as flickering dots, we now see them as layered, complex systems. A flat shimmer becomes a history of nuclear fusion. A color distorted by twinkling becomes a temperature chart with decimal precision. Through the spectrum, we step behind the illusion. Even telescopes on the ground, those still looking up through miles of atmosphere, can pull this information with remarkable accuracy thanks to adaptive optics and clever calibration. Observatories compensate for atmospheric interference by comparing starlight to known references, adjusting their instruments to subtract the flicker and preserve the spectrum. It's a kind of visual alchemy, taking unstable light and revealing its inner structure. This is how we know what stars are made of. It's how we first discovered helium, not on Earth, but in the spectrum of sunlight during an eclipse. It's how we know that stars across the universe follow the same physical laws as those in our own galaxy. And it's how we classify them not by how they look to the eye, but by how they speak through light. It's a bit like tuning into a song that's been playing behind static. The shimmer is still there, but the melody comes through once you learn how to listen. There's something humbling about that. The recognition that even the clearest night sky offers only a version of the truth. That beauty and distortion can live side by side. That the flicker we find so poetic, the trembling light, the sparkle of stars also obscures the message beneath. But that message is still there, waiting, encoded in color and line. And when we finally decode it, the stars speak with clarity. They tell us their temperature, their makeup, their age. They reveal the elements they've created in their cores. They whisper the secrets of their beginnings and hint at how they'll end, all in light, all through the spectrum. So the next time you see a star flickering above the horizon, pulsing through 100 invisible veils, know that its true color is more than what your eyes can catch. Behind the shimmer is a signature. Behind the twinkle is a truth, and that truth, once seen clearly, changes everything. Your eyes are extraordinary instruments, evolved not to see the universe exactly as it is, but to see it in a way that helps you survive. They are built to detect motion in the shadows, to spot patterns in chaos, to track contrast and edge more than color or clarity. What they see is not a raw feed of the world, but a filtered interpretation, an ongoing negotiation between light and brain. This becomes especially clear at night, when the sky fills with tiny lights that seem to flicker, dance, and sometimes disappear entirely, even though the stars themselves never waver. In the dark, your eyes switch modes. During the day, your vision relies on cone cells, photoreceptors that detect color and fine detail. They thrive in bright light, allowing you to read, recognize faces, and distinguish hundreds of subtle hues. But under the stars, the cones retreat, and the rod cells take over. Rods are far more sensitive to light, but they come with trade-offs. They can't detect color, they don't offer much detail, and they respond more slowly to changes in brightness. They're built not for clarity, but for survival, for sensing motion in dim conditions, for picking out the sudden flicker of something moving against the night. This shift is subtle, but powerful. You may not notice it happening, but your vision under starlight is fundamentally different from how you see during the day. Even the shape of your focus changes. Rods are concentrated away from the center of the retina, which means your night vision is strongest, not when you look directly at something, but when you look slightly to the side. That's why a dim star sometimes seems to vanish when you stare at it, only to reappear when you glance away. It's not the star that moved, it's your eyes, handing off the image to the part of your retina more capable of detecting it. When starlight twinkles through the atmosphere, it creates quick, tiny changes in brightness and position. These fluctuations are often too fast and subtle to be perceived consciously, but your eyes still register them. Your brain, always trying to make sense of the signal, may interpret these as motion. A star may seem to vibrate, shimmy, or pulse, not because it's moving, but because your visual system is built to detect movement wherever possible. It errs on the side of caution, preferring false positives to missed threats. In the safety of the night sky, this evolutionary bias becomes a kind of optical illusion, and then there's the persistence of vision, your eyes and brain working together to smooth out flickers into something more stable. This is the same principle that allows movies to work. A rapid sequence of still images becomes a fluid story. But when the flicker isn't regular, when it's chaotic, as with atmospheric scintillation, your brain doesn't know how to stabilize it. Instead of creating smooth motion, it creates jitter. The star appears to flicker wildly, because your mind is caught between correcting for the motion and acknowledging it. The result is a star that seems to dance, even though it's motionless. Brightness plays a role too. Brighter stars flicker more vividly because their variations stand out against the darkness. Dimmer stars may still be affected by the atmosphere, but their flicker falls below the threshold of perception. Your eyes smooth it out, ignore the noise, and present you with a calm, steady point of light. In this way, your perception of twinkling is not just a function of physics, but of psychology. Two people looking at the same sky might see it differently, depending on the sensitivity of their eyes, the sharpness of their vision, or even how well adjusted they are to the dark. The mind adds its own interpretations. A star low on the horizon may flicker in color due to atmospheric refraction, but your brain might perceive it as a flashing beacon, a distant plane, or even something unnatural. Stars near bright objects can seem to vanish and reappear due to contrast effects. A dim star near the moon may be completely invisible until you look away, even though it's still shining. And in moments of stillness, when you fix your gaze on a single point, you may begin to see movement in the periphery, a slow drift, a shimmer, a wobble that isn't really there. These illusions are not failures of your vision, they are features. The eye is built to make meaning from minimal information, to fill in gaps, to smooth over noise. In the absence of clarity, it invents motion, finds rhythm in randomness, adds shape to what is uncertain. It is trying to help you understand the world, even if the result isn't always accurate. In the case of stars, that means turning their steady, ancient light into something dynamic, into flickers and flashes that feel alive. You can't turn this off. Even trained astronomers with years of experience know the feeling of seeing things that aren't quite there. A ghost of movement at the edge of vision, a flare of light that fades before you can name it. The flicker is not just in the star, it's in you. Knowing this doesn't make the experience less beautiful. If anything, it makes it more human. The stars may be constant, but we are not. We are always changing, always adapting, always interpreting. And the sky we see is not just a reflection of space, but a reflection of ourselves, of how we're built, how we think, how we've evolved to perceive. There is a kind of wonder in knowing that what you see when you look up is both real and invented. That the twinkle in a star is shaped not only by air and light, but by the machinery of the body and the poetry of the mind. It reminds you that perception is a collaboration between physics and biology, between sky and soul. And in that dance between the true and the seen, the night becomes something more than darkness pierced by points of fire. It becomes a canvas, painted by light, and by the ways we learn to follow it. The air above you is never still. Even on nights when everything feels hushed and unmoving, no breeze, no rustling trees, no clouds slipping by, there is motion layered high above. Invisible rivers of atmosphere sliding past one another, columns of heat rising from the day-warmed ground, cold pockets sinking, giant flows of wind shearing at different altitudes. Even when the sky looks empty, it is alive with motion. A slow, silent ocean made of gas and light. Jet streams slice through the upper atmosphere like braided currents, thousands of kilometers long and hundreds wide, racing at speeds that would make your eyes water. Beneath them, smaller currents dance in turbulence, eddies and spirals, rolling cells of rising and sinking air. Some are born from the heat of the land, others are stirred by mountains, by ocean waves, by storms that have long since moved beyond the horizon. These layers don't move together, they slip and slide, rub and ripple, creating a quilt of constantly changing density. To the eye, it's all invisible, but to a beam of light, especially something as narrow and ancient as starlight, these differences are immense. When light passes from one medium to another, it bends. That's the principle behind every lens you've ever looked through. And when starlight moves from one patch of air to another air that might be warmer, cooler, denser, or thinner, it refracts ever so slightly, over and over again. A million subtle bends happening across miles of shifting atmosphere. Each star sends its light as a perfect line, a direct vector from where it burned across the gulf of space. But as it reaches our atmosphere, that perfect line becomes a jitter. The light is nudged one way, then another, scattered and reshaped by moving air. And because different patches of atmosphere refract light differently, and because they're always changing, the star's image wobbles, it appears to dance. It flickers in place, it twinkles. On some nights, the dance is gentle, like a soft shimmer on the surface of a pond. On others, it's chaotic, stars flashing, jumping, their light fragmented as if bouncing through a hall of rippling mirrors, and all of it is guided by the state of the air. That's why astronomers talk so much about seeing, not seeing with the eye, but the quality of the sky itself, how stable the atmosphere is, how cleanly it lets starlight through. A night with good seeing is one where the air is steady, where the layers are calm, where turbulence is minimal. The stars shine sharp and still, and telescopes can gather their light with clarity. But when the atmosphere is restless, the stars jitter and blur. A point becomes a smear. A clean image becomes a wavering ghost. It isn't just temperature that causes this. It's the entire architecture of the sky. Jet streams introduce high-altitude chaos, shifting entire layers of air across continents. Thermal currents rise in columns, triggered by warm surfaces cooling off after the sun sets. Even cities, with their pockets of heat and artificial light, push warmth into the sky, adding noise to the flow. The night sky is not merely something you look at, it is something you look through. And what lies between you and the stars is always in motion. That motion can change quickly. A cloudless night can begin calm, then worsen as the atmosphere destabilizes. Or it can start rough and settle into stillness. Sometimes the best views come just before dawn, when the cooling earth has finally stilled the lower layers of air and the stars seem to hold their breath. Other times, a thin jet of warm air slips overhead, and what was once a sharp view turns to soup in minutes. The sky breathes, and starlight moves with it. High above, in the stratosphere and beyond, even more subtle shifts occur. Air bends and compresses in great tidal waves, sometimes driven by planetary rotation, sometimes by solar heating, sometimes by the moon's silent tug. These atmospheric tides don't create wind at the surface, but they can ripple the air far overhead, adding yet another layer of motion to the path of light. And down in the troposphere, where weather lives, even a gentle wind can stir the sky into shimmering motion. You might never notice this during the day. Sunlight overwhelms these effects. The brightness is too great, the sky too evenly lit. But at night, when all you have are tiny points of light piercing the dark, even the slightest shimmer becomes visible. It's like watching a candle through the surface of a pool. The flame never moves, but the water makes it dance. And yet, for all this movement, the stars endure. Their light crosses unimaginable distances to reach you unbent, unshaken, unbroken, until the very last moment, when it meets the restless breath of Earth. That final stretch, just a few dozen miles above your head, is enough to turn a beam into a twinkle, enough to scatter the precision of space into the softness of our sight. There's something poetic in that. The idea that the flicker of a star is not the result of chaos, but of interaction, not disorder, but a conversation between starlight and sky. A dance not of stars making, but of Earth's ever-changing breath. So the next time you step outside and see a star shimmer, remember that what you're seeing is not just distant firelight. You're watching the air above you, the movement of invisible currents, the constant shaping of perception by nature itself. You're watching the sky reveal its structure, not by shadow, but by how it handles the oldest light in the universe. And in that flicker, you are watching motion itself made visible. The air is always moving, and because of that, the stars never stop dancing. Some stars draw your eye immediately, not just because of their brightness, but because of the way they move, shivering, flashing, as if caught in some cosmic strobe. They seem almost alive, pulsing with intensity, burning brighter than the rest. Sirius is one of them. On a clear winter night, it doesn't merely shine, it dances. It flickers red, blue, white, green, as if someone were playing with a prism in the dark. And yet the star itself is perfectly stable, an unwavering source of light. The shimmer is not from the star, but from the way it's framed by our sky. Sirius is the brightest star in the night sky, nearly twice as bright as the next closest contender. That intensity makes every fluctuation more visible. Where a fainter star might flicker softly, quietly, Sirius blazes through every disruption in the air. Its twinkle becomes exaggerated. It flashes boldly, where others only quiver. It's not that it twinkles more often, it's that you can't help but notice when it does. The brightness of a star acts like an amplifier. Even tiny shifts in its position or brightness become easy to detect when the contrast against the dark sky is strong. Our eyes, tuned for change, latch onto the fluctuations, and the brighter the source, the more dramatic the illusion becomes. Sirius, brilliant and close, becomes a kind of mirror for the atmosphere's invisible motion. It shows you what the air is, doing with startling clarity. But it's not just brightness that shapes the twinkle. It's position. Stars that hover low near the horizon seem to shimmer more than those that sit directly overhead. It's not a trick of the angle, it's physics. When a star is low in the sky, its light has to travel through a thicker slice of the atmosphere to reach you. That means more turbulence, more temperature layers, more chances for refraction to bend the beam. Like shining a flashlight through rippling water, the distortions grow stronger the longer the path. Imagine looking at a coin at the bottom of a pool. When you peer straight down, it might look slightly off, but still recognizable. But try looking from the side, through more water, and the coin begins to shift, to ripple, to lose its shape entirely. The same thing happens with starlight. High-altitude stars cut a direct path through the sky. Low ones skim along the edge, passing through more of the air's unstable layers, picking up every little wobble along the way. This is why stars near the horizon seem to flash wildly in color. Their light passes through so much atmosphere that the different wavelengths begin to separate. Shorter wavelengths, blues and violets, are bent more than reds. If the air is moving unevenly, those colors reach your eye in flickering succession. You might see a flash of red, then green, then back to blue, all in a second. It's not that the star is changing, but that the atmosphere is teasing apart the light and letting it recombine chaotically. The angle matters more than you might think. Just a few degrees of elevation can make the difference between a steady point of light and a frantic glitter. Astronomers have known this for centuries. That's why telescopes are often aimed high toward stars closer to the zenith, where the air is thinner and more stable. Observations taken closer to the horizon are more likely to be distorted, blurred, and scattered. There's also the matter of how the air itself behaves at different altitudes. High-altitude turbulence up near the jet streams and stratospheric waves tends to cause gentle, widespread distortions. These affect many stars at once, creating a soft shimmer across the sky. But lower-altitude turbulence, caused by ground heat or local air currents, can have a more dramatic effect on stars near the horizon. It's localized, unpredictable, and often sharp. A single column of rising warm air can make a star dance wildly, even if everything else in the sky seems still. Sirius, being both bright and often low in the sky during its prime viewing season, gets hit by all of these effects. Its light shines like a spotlight through the atmospheric mess, and so, while it remains a steady, massive sun over 8 light-years away, we see it as a flickering gem, sometimes sparkling, sometimes pulsing, always moving. Other stars do this too. Arcturus, Vega, Capella, each of them flickers in its own way, depending on its brightness, its position, and the conditions of the sky. Some are steady sentinels, barely wavering. Others tremble like candle flames caught in a draft. Even faint stars can twinkle dramatically if they hover low enough on the horizon, their light scraping through the thickest, most unstable parts of the atmosphere. And yet, this shimmering is more than distortion. It's a kind of translation. The atmosphere takes a pure signal from space, millions of years in transit, and turns it into something dynamic and ever-changing. The same way wind through leaves creates rustle, or water over stone forms ripples. The twinkle isn't noise. It's a signature of the world we live in, a reminder that Earth is alive, that the air around us is always in motion, always shaping what we see. So when you see one star flickering more than the rest, know that it's not alone in the sky. It's simply more exposed to the dance of the air. It is brighter, perhaps closer to the horizon, perhaps shining through a corridor of unstable sky. But it is also a guidepost, letting you glimpse the otherwise invisible currents flowing above. You're not just watching light, you're watching motion, depth, refraction, heat. You're watching the story of your own atmosphere, written in the flicker of something unimaginably far away. To an astronomer, the word seeing means something very different than it does to the rest of us. It doesn't refer to eyesight or perception or awareness. It refers to the sky itself specifically, to the stability of the atmosphere through which that sky is observed. It's a strange kind of measurement, less about brightness or color or even clarity, and more about behavior. How much does the atmosphere shimmer? How much does it warp and wiggle the starlight coming through it? Good seeing means a steady, still sky. Bad seeing means a sky in motion, a sky that dances too much to let you study what lies beyond. Stargazers have always known that some nights are better than others. Even before there were telescopes, even before we had a word for the phenomenon, people would notice the difference. Some nights, the stars would sit still, gleaming like pearls on velvet. Other nights, they'd wobble and jitter and flash, refusing to hold still long enough to be admired. That wasn't the stars. It was the air. The term seeing evolved as a way to quantify this, an attempt to measure something ephemeral. It describes how sharply a telescope can focus starlight, how much that light is smeared or scattered by turbulence. A night with excellent seeing might allow you to resolve the fine structure of Saturn's rings, the tight spiral of a distant galaxy, or the delicate separation of a binary star. But when seeing is poor, even the brightest stars swell into fuzzy blobs, details melt away, the universe blurs. Ironically, it's not always obvious to the naked eye when seeing is bad. A sky can be crystal clear, no clouds, no haze, no moonlight, and still be turbulent. The atmosphere may be filled with fast-moving layers of air, each with its own temperature and density, refracting light in chaotic directions. The stars will still shine, but through a telescope, they'll boil. Their images will dance and distort, impossible to pin down. In extreme cases, even long exposures can't fix the mess. The light simply won't hold still. So astronomers rate seeing on a scale. There are various systems, but the principle is the same. Smaller numbers mean better conditions. A night with 1 arcsecond seeing is remarkably still. A star's light is being smeared out only a tiny amount, just 1 arcsecond of sky, which is roughly the apparent size of a penny viewed from 2 miles away. If seeing worsens to 3 or 4 arcseconds, the star's image swells, fine details vanish, and precision vanishes with it. To combat this, astronomers have developed tools and tricks to work around the atmosphere. One of the oldest is simply elevation. Observatories are often placed on mountaintops, where the air is thinner, drier, and less turbulent. From high above sea level, you skip the thickest, most unstable parts of the atmosphere. You avoid much of the ground heat that causes rising currents, and you're often above the clouds entirely. Places like Mauna Kea in Hawaii or the Atacama Desert in Chile weren't chosen for their beauty, but for their stability. But even at high altitudes, the air still moves. So came the next innovation: adaptive optics. These systems work by constantly measuring how the atmosphere is distorting incoming light and then correcting for it in real time. They do this using a guide star, either a bright natural star or one created by shining a laser into the upper atmosphere to excite sodium atoms, forming a glowing point of reference. A high-speed computer monitors how that light is being bent and flexed, and then adjusts a special mirror to cancel out the distortions. The mirror itself isn't solid in the traditional sense. It's flexible, often controlled by hundreds of tiny actuators that shift its surface by microns, thousands of times per second. It's a dance, an intricate, invisible ballet between air and optics. The atmosphere tries to warp the light, and the telescope mirrors warp in response, reshaping themselves to bring the stars back into sharp focus. With adaptive optics, ground-based telescopes can achieve clarity that rivals even space-based observatories. It's a triumph of engineering over nature. Other technologies help too. Interferometry allows multiple telescopes to work together, combining their signals to create a virtual instrument with a resolution far beyond what any single dish could provide. Speckle imaging takes a rapid series of short exposures and stitches together only the clearest moments. And software, always improving, helps to process and sharpen images after the fact, removing blur introduced by turbulence. Yet even with all this, the atmosphere remains a challenge. It is a living, moving medium. It cannot be stopped, only worked with, corrected for, modeled, and measured. Every observatory logs the seeing conditions for every observation, not as an afterthought, but as a vital piece of data. Good science depends on good seeing, and good seeing depends on a sky that, just for a moment, holds still. There's a kind of beauty in this fragility, in knowing that our view of the cosmos depends on a thin, trembling shell of air, that between us and the stars lies a restless sea of gas, breathing, flowing, shifting endlessly. It's humbling to think that a star's light can cross a galaxy untouched, only to be scattered by a warm breeze in the final milliseconds of its journey. But it's also a reminder of our ingenuity, of how much we've done to peer through that distortion, to correct for it, to find stillness in the shimmer, and to keep reaching again and again for a better view of what lies beyond. Seeing may begin in the eye, but in astronomy, it ends in the sky. And the clearer the sky, the more of the universe it reveals. If you were to stand on the dusty plains of Mars, under a sky tinted rust red by suspended particles, you'd notice something curious about the stars. They don't twinkle not the way they do from Earth. The air is too thin. The Martian atmosphere, though real, is only about 1% as dense as Earth's, and turbulence doesn't have much to play with. A star's light arrives nearly as clean as it would in space, barely bent, hardly scattered. It shines steadily, like a pinprick of truth hanging in the stillness. There is no shimmer, no dance, just quiet light, delivered almost exactly as it left its source. Mars offers clarity, but not comfort. Its skies are often hazy with dust, and the same particles that color the sunsets in copper tones can also obscure the stars. But when the air clears, the view is breathtaking in its sharpness. You wouldn't see them twinkle, but you would see them pure, so pure that even a simple telescope might reveal things that, from Earth, remain hidden behind a veil of atmospheric noise. On Mars, the stars do not flicker with life. They wait, fixed and unmoving, untouched by the breath of an absent wind. Now imagine a night on Titan, Saturn's largest moon. The sky there is not red, but a hazy, golden orange, thick with a nitrogen-rich atmosphere laced with methane. It is cold, colder than anything you've ever felt. Yet the atmosphere is denser than Earth's. This thickness could, in theory, create more pronounced twinkling, depending on how the layers move. But the haze is so thick, so pervasive, that stars may be nearly impossible to see at all. Light has to struggle to penetrate that chemical fog. And yet, if it could, and if you looked up during a rare moment of clarity, you might see a shimmer, a flicker, filtered through a golden curtain, refracted by a world wrapped in hydrocarbon smog. On Titan, the air is heavy but slow. The gravity is weaker than Earth's, so the atmosphere lingers close to the surface, pooling like syrup. This density might amplify some types of atmospheric distortion, but much depends on temperature gradients, wind shears, and the layering of gases. We don't yet know if Titan's air behaves in such a way that stars would twinkle more or less than on Earth. But we can imagine it, a sky not filled with sparkle, but with a diffused, dreamlike glow, like stars seen through amber. And then there's Venus, a planet that, on the surface, is less a home and more a furnace. Its atmosphere is a crushing blanket of carbon dioxide, with sulfuric acid clouds and temperatures hot enough to melt lead. The density is enormous, 90 times Earth's at sea level. A star's light trying to punch through that atmosphere would be bent and twisted in ways we can scarcely predict. But visibility is the issue. Those clouds are so thick, so opaque, that the surface of Venus is in perpetual twilight. The sun itself is barely a suggestion through the murk. But let's say you rose above the clouds, maybe in a balloon, floating in the more temperate layers 30 miles up, where pressure and temperature are almost Earth-like. Up there, the atmosphere thins, and the clouds begin to part. Would the stars twinkle through the Venusian sky? Possibly, though the refraction might be smoother, stretched by the uniformity of high-altitude haze. You might not see the sharp, playful flicker of Sirius, but instead a slow, molten shifting, as though the stars were made of fluid glass. It all comes down to the atmosphere. Twinkling is not universal. It is an accident of air, a byproduct of moving gases wrapped around a rocky shell. No air, no twinkle. On the moon, where no atmosphere exists, the stars don't shimmer at all. They shine with an eerie constancy, crisp and eternal. Astronauts on the lunar surface, had they taken the time, could have looked up and seen stars as fixed as ancient carvings. No flutter, no dance, just light, unbent, unchanged, raw. Every world tells a different story through its sky. On planets with no atmosphere, stars are steady, and unforgiving. On those with thick, restless air, they can flicker, sway, and vanish. The nature of the twinkle, its strength, its color, its rhythm, is dictated by wind and heat, by pressure and motion. It's a reflection not of the stars themselves, but of the planet doing the looking. If we imagine alien astronomers' creatures living under strange suns and stranger skies, their experience of the stars would be wildly different. Some might see only dim glows, fighting through storms or veils of perpetual cloud. Others might see stars in such clarity that twinkling would be considered a myth, a poetic invention of beings who live beneath dancing air. A planet with a calm, cool, stable atmosphere might offer views of such perfection that the stars appear etched onto the dome of the night, unmoving for hours, unbroken by the world below. But imagine a world where the atmosphere is restless, layered, active, a sky that breathes like ours, but with thicker lungs, deeper drafts, taller clouds. There, stars might not just twinkle, they might pulse, shimmer, flare. They might become alive in the air, changing shape and hue with every breath of wind. To live under such a sky would be to live under a story in motion, a tale written in light and weather and time. Twinkling, in the end, is not just a physical phenomenon. It is a form of perception. It is a collaboration between a beam of ancient starlight and the layers of air it must traverse. And each world, with its own atmosphere and weather and winds, offers a different collaboration, a different lens through which the stars must speak. From Mars, the stars whisper in stillness. From Titan, they glow behind a veil. From Earth, they flicker like fire. Each version is true. Each sky sings its own song. And in the shimmer, in the silence between flickers, we find not just the stars, but the world we're standing on. From Earth, a star's twinkle might seem like little more than a poetic distraction, a shimmering detail that decorates the night, lovely but meaningless. But sometimes, tucked inside that flicker, hidden in the slight dips and stutters of its light, is a signal, a clue, a whisper that something else is there, something orbiting, circling, passing between us and that distant sun, something unseen but not undetectable, a planet. The method is called transit photometry. It relies not on the grand sweep of telescopes or the sharpness of images, but on the most subtle changes in brightness, a tiny dip in a star's light as something moves in front of it. That something might be a planet, perfectly aligned in its orbit to cross our line of sight. The dip might last only a few hours. The amount of light lost might be less than 1%. But if it happens regularly, rhythmically, like the beat of a drum in deep space, then we know we've found something, a world, distant and dark, revealed only by its shadow. For astronomers, this is where the twinkle becomes both challenge and opportunity. Atmospheric scintillation, the very thing that causes a star to shimmer, also makes it harder to detect those minute changes in brightness. The atmosphere introduces noise, fluttering the signal, bending and brightening the light in random ways. That's why so many exoplanet hunting missions are done from space. There, above the turbulence, stars don't twinkle. They hold steady. Their light is unbroken, pristine, and in that stillness, the smallest changes can be seen. The Kepler Space Telescope changed everything. Launched in 2009, it stared at a single patch of sky for years, monitoring the brightness of over 150,000 stars. It didn't take pictures the way most telescopes do. It measured light, moment by moment, waiting for it to dip. And in that ocean of data, it found thousands of candidates. Some were hot gas giants, orbiting close to their stars. Others were smaller, rocky, potentially Earth-like. Each one was a discovery not made by seeing the planet directly, but by watching how it briefly stole some of its star's light. But even from space, false positives can creep in. Binary stars, for instance, two suns orbiting each other, can mimic a planet's transit if their alignment is just right. So can stellar activity, flares, spots, or intrinsic brightness fluctuations. Some twinkles aren't caused by planets at all, but by the stars themselves. Understanding the nature of a star's flicker becomes critical. Is it steady over time? Does it pulsate? Does it spin with dark patches that drift across its surface? All of this needs to be untangled before we can be sure that a planet is hiding there. That's where follow-up observations come in, some from the ground, some from space. Once a promising candidate is spotted, astronomers study the star's light more carefully. They look at its spectrum, its motion, its temperature. If the dimming is regular and the star behaves as expected, the case for a planet strengthens. Sometimes, telescopes like TESS or James Webb step in, adding precision and depth. And slowly, the picture sharpens. A shadow becomes a planet. A dip in brightness becomes a name on a growing list of exoplanets, worlds that orbit suns far beyond our own. There's something hauntingly beautiful about the idea that a planet can be discovered not by its presence, but by its absence, not by its light, but by the light it briefly takes away. That the great unknown of space can be explored not just through bold voyages, but through careful watching, quiet measurement, patience, and that shimmer, the twinkle we see with the naked eye, plays a part in that story. On Earth, it obscures. In space, it disappears. And its absence becomes the very thing that reveals. Even on the ground, some astronomers still chase these dips, using clever techniques to subtract the atmosphere's influence. They take thousands of measurements, average out the noise, apply algorithms that filter out turbulence. They build observatories at high altitudes where the air is thinner, the twinkle softer. They wait for nights of exceptional stability. And on those rare nights, they watch the stars dim, not because of the wind, but because a planet is crossing. We've discovered thousands of these worlds. Some are strange and massive, with orbits so close to their stars that their years last only days. Others are cool and temperate, basking in just the right amount of light. A few lie in the habitable zone where liquid water might exist, where atmospheres might swirl, where perhaps, someday, life might be found. All of them began as flickers, as twinkles, as numbers in a stream of light. It's easy to forget how delicate these discoveries are. How much of astronomy is about interpretation, reading the language of light? How much of what we know about the universe has come not from grand images, but from small changes, dips, wobbles, flickers. So the next time you see a star twinkle, imagine what might be moving in front of it. Not just dust or air or cloud, but an entire world. One with valleys and mountains and skies of its own. One we cannot see, but know is there because of how it gently interrupts the light. That flicker you're watching could be hiding an ocean, a storm, a sunrise, a signal. Some stars flicker not because of air or illusion, but because it is their nature to do so. Their brightness pulses with a rhythm not imposed from outside, but born from within. These are the stars that keep time, that count the silence between seconds not with ticking gears or pendulums, but with light. Some do it subtly, gently, like a heartbeat echoing across space. Others do it with such precision and regularity that they rival our best atomic clocks. And in the quiet, rhythmic flash of their light, something astonishing becomes clear. Not all twinkling is a trick of the eye. Some is a message. Pulsars are among the most extraordinary of these cosmic timekeepers. They are the remnants of once massive stars, collapsed in on themselves until their cores became neutron stars, city-sized spheres of matter so dense that a single teaspoon would weigh as much as a mountain. These objects spin with incredible speed, sometimes hundreds of times per second, and their magnetic fields channel beams of radiation from their poles, sweeping across space like lighthouse beams. If one of those beams points toward Earth, we see it flash. On, off, like a cosmic metronome ticking out the moments. They don't twinkle like stars in the atmosphere. they blink with perfect mathematical certainty. Their flashes are so regular that early astronomers, unsure of what they were seeing, dubbed the first discovered pulsar LGM-1 for little green men. They thought perhaps, for a moment, it might be a signal, and in a way, it was. Not from aliens, but from the universe itself, telling us that the collapse of a star could become not just an ending, but a rhythm, a heartbeat in the dark. Then there are variable stars, stars that truly change in brightness, not because of interference, but because of something internal. Some are unstable giants that expand and contract, their outer layers swelling and cooling before tightening again, like the slow breath of something enormous. Others are locked in binary systems, orbiting close to stellar companions whose gravity distorts them, pulling at their light like tides on a shore. As they move, the light changes, it dims, it returns. It follows a pattern, a wave written in time. Cepheid variables are one of the most famous kinds. Their brightness rises and falls in a regular cycle, and the length of the cycle is directly linked to their true luminosity. That makes them invaluable tools for measuring distance. If you know how bright a Cepheid truly is, and you measure how bright it appears, you can calculate how far away it must be. That discovery turned them into beacons, standard candles, lighthouses scattered through the galaxy and beyond, helping us chart the shape and scale of the universe, and all because they flicker, not from air or illusion, but from within. The key difference is control. Atmospheric twinkling is chaotic, random variations imposed by the ever-moving shell of gases around Earth. You can't predict exactly how a star will shimmer from one moment to the next, but pulsars and variables operate on their own clocks. Their brightness changes according to laws of physics that are repeatable and precise. When a pulsar flashes, it does so with a period you can set your watch by. When a Cepheid pulses, its timing tells you its power, and its power tells you where it lies in the vastness of space. These stars don't twinkle in the poetic sense. They flash, they breathe, they signal, and those signals are not distractions, they are data. From them, we learn not just how stars live and die, but how far away they are, how fast the universe is expanding, and how matter behaves under pressures we can scarcely imagine. The blink of a neutron star can tell us about gravity. The pulse of a red giant can help us measure the age of galaxies. In a way, these are the stars that speak. Their light is not static, but dynamic. It changes, it moves, it carries information. And if you know how to read it, how to track the intervals and measure the dips, you begin to understand that the sky is not still at all. It's alive with rhythm, with time. When you look up at night and see a star twinkle, it's easy to dismiss it as atmosphere, and often that's all it is. But hidden among those ordinary flickers are extraordinary ones, twinkles with intention. Some stars dim not because of turbulence, but because something passed in front of them. A planet, perhaps, or another star. Some brighten not because of illusion, but because they're exploding or cooling or entering some new phase of their long stellar evolution. Every variation in brightness is a chance to learn something, a chance to see the star not just as a distant light, but as a body physical, dynamic, real. These aren't just pinpricks in the sky. They are clocks, signals, warnings, invitations. They are timepieces. Some spin like tops and flash like strobe lights. Others pulse slowly, steadily, like a giant sleeping in deep space. Some flicker once and vanish forever, their light swallowed in collapse. But when they flicker again, when they return on schedule, you begin to trust them. You begin to see them not as decoration, but as markers, signposts in the night. Not all twinkling is illusion. Some of it is truth, disguised as a blink, a whisper, perfectly timed. During wartime, clarity can mean survival. The difference between a message received and one lost to silence might be measured in milliseconds, in subtle warps of signal, in flickers too fast for the eye, but not too small for the machines that carry our voices across the world. In the invisible threads that link satellite to base station, aircraft to command center, lies a phenomenon older than any technology we've made, yet ever present in the digital lattice of our world. Scintillation, what we often call twinkle, has found its way into the very core of our modern systems, not as a poetic detail, but as a problem to solve and a tool to wield. Long before it was a romantic mystery of the stars, twinkling was an obstacle. When radio signals travel between Earth and space, they pass through the same turbulent layers that distort starlight. But unlike light, which twinkles only when seen from the ground, radio waves can flicker all the way through their journey. As they pass through layers of uneven plasma in the ionosphere, where solar radiation stirs charged particles into a restless sea, they scatter, refract, and interfere with themselves. The result is not a visible shimmer, but a breakdown in clarity, dropouts, lag, a voice cut short, a target misread. Military communications, particularly those relying on satellites, must contend with this. A single flicker can scramble coordinates, blur radar signatures, or muffle commands. In early space missions, engineers were surprised to find that even strong signals could vanish momentarily, swallowed in patches of disturbed ionospheric activity. These interruptions weren't random, they followed solar cycles, atmospheric tides, and the rhythms of magnetic storms. Understanding the twinkle meant learning to anticipate these invisible disruptions, to predict where and when they would strike. But the military doesn't just try to eliminate scintillation, it studies it, it listens. Because that flicker contains information about the air it passed through, the storm that stirred it, the solar flare that sparked it. By measuring how a signal flickers, analysts can reverse engineer the conditions it traveled through. They can track solar weather. They can detect electronic interference. They can even sense the presence of an object or anomaly, something in the way that bent the beam, however briefly. In this way, twinkling becomes not a flaw, but a fingerprint, a diagnostic tool. During conflicts, the ability to track scintillation has been used to determine the presence of jamming devices, to infer weather conditions in denied areas, to identify weak points in enemy communication infrastructure. The same principle applies to GPS technology. Your phone's ability to pinpoint your location relies on clean signals from satellites orbiting tens of thousands of kilometers away. But when those signals pass through turbulent regions of the ionosphere, especially near the equator or during solar storms, they scatter. Your position jumps. Navigation falters. Aircraft and ships must correct for this in real time, and so the maps they follow must account for the twinkle, even if the passengers aboard are never aware of it. In response, global monitoring systems have been built to track radio scintillation, constantly watching the sky not just for signals, but for how they waver. These systems chart the invisible weather of the upper atmosphere, giving forewarning of disruptions that might affect navigation, banking, communication, or reconnaissance. And increasingly, artificial intelligence is being trained to interpret those patterns, to learn the language of the flicker, and to spot when something unusual is hiding in the noise. Twinkle becomes code. The technology isn't confined to defense. In radio astronomy, scientists study the flickering of distant quasars to probe the space between galaxies. Their twinkle reveals the density of interstellar clouds, the movement of invisible gas, the reach of magnetic fields. In telecommunications, engineers study multipath scintillation, the way a signal bounces off buildings, terrain, and clouds to design more efficient networks. In deep space tracking, agencies like NASA must constantly adjust for the flickering of signals sent from far-off probes, calibrating for solar wind and galactic dust. Even the most distant parts of our universe still twinkle, not in color, not in sparkle, but in how their messages warp and wobble on their way to us. And in every flicker, there's a story. Of course, not all of it is dramatic. Sometimes, scintillation is merely an annoyance, a glitch in a call, a hiccup in a satellite feed, a delay in data. But even then, it serves as a reminder we are not speaking across a vacuum. Every signal, every beam, every pulse of information must journey through an ocean of movement, through air and plasma and space itself, through storms of ionized particles, through waves of gravity and bursts of radiation. Twinkle isn't just for the stars, it lives in the very fabric of how we connect. It complicates, it reveals, it warns. And as our technologies reach further, as our satellites orbit faster and our probes drift deeper into the black, the flicker becomes more important because there will always be something in the way. A current in the air, a ripple in space, a warble in the beam. The stars may no longer guide our ships, but the flicker of a signal still charts our course, still tells us something moved, something changed, something passed between. In the heart of battle, in the silence of deep space, in the quiet stream of ones and zeros, scintillation endures, not just a shimmer of light, but a shimmer of knowledge, high above the desert plateaus where the night air runs cold and the silence carries weight. Observatories wait. Their domes crack open like ancient shells, revealing eyes of glass aimed skyward, trained on the stars. But what they seek isn't just light. It's stillness, clarity, a kind of cosmic quiet that Earth rarely grants. Because to see the stars as they truly are, not shimmering, not shifting, not veiled by the breath of our atmosphere, requires more than a telescope. It requires a way to calm the flicker, and so begins the quiet war against Twinkle. For centuries, astronomers were forced to contend with the shimmering distortions of Earth's air. No matter how perfect the lens, how vast the mirror, the atmosphere blurred the view. The dance of hot and cool air layers above us twisted the starlight into chaotic patterns, smearing fine detail into noise. A distant galaxy might appear soft and swollen. A binary star might blur into one. The atmosphere made giants look like ghosts. But then, we learned how to tame it, not by removing the air, but by predicting its ripple. The technique is called adaptive optics, and it is one of the most delicate feats of modern astronomy. At its heart is a simple idea. If you can measure how the air is bending the light, you can bend it back. Not after the fact, not in post-processing, but in real time, hundreds of times per second, like sculpting starlight while it still travels. The system begins with something that shouldn't exist, an artificial star. From the dome of the telescope, a laser is fired upward into the sky. It vanishes into the dark, climbing to a specific altitude, usually about 90 kilometers up, where it excites a thin layer of sodium atoms naturally present in the upper atmosphere. These atoms glow in response, creating a point of light that, to the telescope, looks like a star. But this star isn't real. It's a reference, a controlled flicker. As the light from the laser star returns through the same shifting air that warps the light of actual stars, it carries the fingerprint of the distortion with it. Wavefront sensors inside the observatory analyze the returning light, mapping the precise deformations caused by the atmosphere, how each column of air bent or delayed the beam. That information is fed to a deformable mirror, a surface capable of flexing and changing shape thousands of times a second. It responds instantly, counteracting the warps in the wavefront by reshaping itself in the opposite direction. The result is astonishing. Light from real stars, entering the same column of air, is corrected in real time. The flicker is stilled, the shimmer fades, and suddenly, the universe sharpens into focus. A star that once danced like candlelight becomes a pinprick of precision. A galaxy, once smudged by air, resolves into arms and edges. It's not just clarity, it's revelation. Without adaptive optics, much of the fine detail in the universe would remain hidden behind atmospheric veil. Features on exoplanets, the shape of black hole environments, the dust lanes that thread through newborn galaxies, all would blur into approximation. But with this technology, Earth-based telescopes can now rival, and in some cases exceed, the sharpness of space telescopes without ever leaving the ground. It is an elegant irony. We correct the chaos of nature by mimicking it. A fake star guides us to real ones. A flicker becomes a map, and mirrors, once fixed and passive, become responsive, breathing surfaces like instruments tuning to a song only the air can sing. But adaptive optics doesn't work alone. It requires quiet skies, high altitudes, low humidity, and the patience of night. Even with perfect corrections, the system must adjust to every breeze, every gust, every tiny pulse of thermal current rising from the land below. It is like playing a violin while standing on a shaking bridge, reading the vibrations not as noise, but as cues. Some systems have grown even more advanced. They use multiple lasers to create a constellation of artificial stars, allowing for three-dimensional models of the turbulence above. With these, they can correct across wider fields of view, bringing more of the sky into crystalline focus. Future observatories, like the extremely large telescope being built in Chile, will depend on these constellations to tame their unprecedented apertures. Without adaptive optics, their massive mirrors would be blinded by the very atmosphere they stand beneath. This isn't just a technical achievement, it's a philosophical one. For all of human history, we accepted the twinkle of stars as part of their nature, as though it was something they did, not something we imposed. Twinkle became poetry, mystery, a symbol of distance, of magic, of something unreachable. But now we know. The stars don't flicker for themselves. They flicker for us because we look through air. And so we built a way to look again, to peel back the shimmer and see what's truly there. Stillness, after all, is not absence. It's precision, a silence of distortion. And in that silence, detail emerges. The edge of a scrav, crater on a moon 2 galaxies away, the flicker of an exoplanet crossing its star, the soft glow of a forming star wrapped in its cradle of dust. All of it made visible not by pushing through the sky, but by listening to it, by learning its distortions so completely that we can speak its language backward. In doing so, we didn't silence the twinkle. We translated it, and from that translation came vision, not just sharper images, but clearer understanding. It begins with a glance upward, a pause in the dark, the slow turning of a child's head toward the stars. Maybe it's a quiet evening on a back porch, or the hush that follows a story told by firelight. Maybe it's the end of a long walk, the breeze soft, the sky clear, and there they are, those tiny flickers stitched across the black, shimmering like they're alive, like they're watching back. They are too far to touch, too old to know, too bright to ignore. And even if we now understand that their twinkle is not a trait of the stars themselves, it doesn't make it any less beautiful. If anything, it makes it more. Because the twinkle is ours, born not in the heart of a star, but in the spaces between, in the thin blue line of air that hugs our planet, in the warmth and wobble of moving winds, in the constant churn of Earth's breath. It's an artifact of perception, a wrinkle in the lens, and yet it has inspired wonder for as long as we've been looking up. Before we knew of thermodynamics or redshift or nuclear fusion, we knew the shimmer. Before we split atoms or sent probes beyond the moon, we whispered poems about it. Songs, prayers, wishes. Twinkle, twinkle, little star. We teach our children, not because the physics is correct, but because the feeling is, because there is a kind of comfort in believing that the stars dance for us, that the cosmos responds, however gently, to our gaze. Even now, with telescopes that can subtract the flicker in real time, with sensors that detect light, too faint for the human eye, we still step outside and search for that familiar sparkle. It's no longer necessary for navigation or survival. It's not even accurate, but it still means something. The shimmer remains a reminder that we are looking through something, not just at something, that we are small and grounded and human. The twinkle tells a story about distance, not just in space, but in understanding. There was a time when stars were believed to be holes punched in the firmament, or lanterns carried by gods, or souls suspended in heaven. They flickered because they were alive, or magical, or closer than they appeared. But now we know they are suns, endless nuclear furnaces, some so large they could swallow our entire solar system, some so far that their light began traveling before humans walked upright. The romance of that shimmer doesn't vanish under the weight of science. It deepens, because now we know what that twinkle had to travel through. We know the countless miles it crossed through dust, through gravity wells, through magnetic fields, and the debris of forgotten comets. We know how it was bent, delayed, shifted, and finally, how it danced through the turbulent layers of our own atmosphere, distorted by air, warmed by a day's sunlight, or stirred by a passing storm. That journey ends in a flicker, a tiny fluttering wink in the sky, and we still watch it. We look up and imagine other eyes looking up from other worlds, wondering the same things. We look up and send signals into the dark, hoping someone, somewhere, sees our flicker too. Perhaps they will mistake it for a star. Perhaps they will know it's a planet. Either way, it will shimmer. It will pulse. And maybe that's the only language we truly share: light, seen from afar, trembling with motion. The twinkle also holds a certain fragility. You have to be in the right place to see it. Far from city lights, far from pollution, under clear skies and quiet winds. As our world brightens, as artificial light spills into every corner, that shimmer becomes harder to find. Some children grow up without ever seeing a star properly twinkle. To them, the sky is static, dim, silent. And so the flicker becomes precious. Not just a curiosity of physics, but a vanishing heritage. A kind of memory shared across generations, the same flicker their ancestors saw when they built pyramids or mapped the sea or waited out winter's long dark. The same flicker they whispered wishes into, or asked questions of, or used to mark the turning of the year. It is one of the last natural illusions we can believe in without harm. The knowledge that it is an illusion doesn't spoil it, it shapes it. Knowing that the twinkle is a trick of the air doesn't make it less meaningful, it makes it more human, because it means we are part of the picture. The shimmer doesn't happen without us, without our atmosphere, without our presence. The stars shine on their own, but the twinkle, that's Earth's signature. That's us. Maybe that's why we hold on to it. Even in metaphor, we say someone has a twinkle in their eye. We call cleverness a spark. We describe hope as a glimmer. We reach for the language of light to describe what's bright inside us. Fleeting, yes, delicate, hard to define, but real, true, felt. The stars may not truly twinkle, but we do.